For group homework 1, question 1, the question is asking for the pH of the solution at 25 degrees Celsius. We are given 0.01 molar of a strong base. So first off, what we want to do is use this formula. With this formula, we'll plug in the concentration of a strong base, which is given here, which is 0.01. So we'll plug that into the equation. And then we'll plug it into our calculator. So negative log 0.01. And that's going to give us an OH value of 2. However, the question asks for the pH. So to be able to get the pH, we're going to have to plug it in, the OH value, into this formula. So we'll subtract 2 from both sides, and that will give us a pH value of 12. That's our answer.
So for homework number 1, I have number 2 to do. So it asks about the dissociation ratio of the first dissociable proton of phosphoric acid at pH 2.6, given the pKa is 2.6, or the Ka is 6.92 times 10 to the third. So for this problem, I basically just wrote everything out. So I'm just going to kind of like rewrite it from what is actually in the question, and then I'm going to go step by step and explain how I got that. So let me just write this out really quickly. Okay, so it mentions that the pH is going to be 2.16. First of all, let me write out this as well. pH equals pKa plus the log of, sorry guys, I'm left-handed. Okay, so this is basically what we're going to use, but we're going to kind of use this towards the end for the dissociation ratio. So 2.6 is the pH, and then the given pKa is also 2.16. Sorry, I mistakenly said 2.6. 2.16 pH, 2.16 pKa. Kind of just like plugging the equation in here. Okay, so 2.16, 2.16, those kind of cancel out. So that's going to make it 0. Okay, and then we go on to try to, go ahead and do the dissociation ratio, or what would lead to the dissociation ratio. Just kind of like I said, just rewriting it. It's kind of like a plug and chug situation here. This is going to equal 10 to the 0, which is going to equal 1. Then next we have over HA again. So also just equals 1. That's just simplifying that. And then we're just going to kind of go just trying to get to the dissociation ratio, essentially. That equals 1, and that equals 1 as well. So here's where our dissociation ratio comes into play. So we know that A is 1. So let's put that. And then we have another one plus HA. Okay, so that equals 1 right here. And then that's 1 plus 1, which equals 2. So 1 over 2 is 1/2. Or 0.5. And those are my steps.
Doing chapter 2 homework number 3. So what we're trying to find is the pH with our given pKa as well as Ka. So we start off with 0.04 moles of benzoic acid. We have our given pKa, which equals 4.2. Sorry. And our Ka, which equals 6.31 times 10 to the minus 5. So, first thing we're going to do is figure out what is our HA. Our HA is 0.04 minus x. Okay, now we're going to take that equation and we're going to say x times x all over 0.04 minus x is equal to our Ka. 31 times 10 minus 5. Of course, we multiply that out. We get x squared over 0.04 minus x still equals our Ka. Alright. So now what we're going to do is we're going to multiply. We want to get our x squared by itself. So we're going to multiply 0.04 minus x on the bottom and on the top. So we have x squared. Well, no, on both sides the equal sign. I'm sorry. X squared over 0.04 minus x times 0.04 minus x. It's going to cancel. Equals 6.31 times 10 to the minus 5. Also times 0.04 minus x. Then we multiply that out as well. And we get x squared equals 2.524 times 10 to the minus 6. Oh, it doesn't go over anymore. Hold on, let me move this. X squared equals 2.524 times 10 to the minus 6 minus 6.31 times 10 to the minus 5 times x. So then we're going to subtract 2.524 times 10 to the minus 6 from both sides. And we're going to add 6.31 times 10 to the minus 5 on both sides. So that will give us an equation of x squared plus 6.31 times 10 to the minus 5 minus 2. Forgot my x. So sorry. There we go. Minus 2.524 times 10 to the minus 6. Now, what we'll notice is this is now in the form of ax squared plus bx plus c, which is a form that we can use to plug into our quadratic equation. So the quadratic equation is as follows. I like to write it out so I'll know what it is when I'm studying. So x equals negative b plus or minus the square root b squared minus 4ac all over 2a. So when I'm working this problem out, I like to split it up. And I like to find different parts of the quadratic equation rather than just plugging all the numbers in at once. So our a equals 1. Our b equals 6.31 times 10 to the minus 5. And our c equals negative 2.524 times 10 to the minus 6. Can't forget that minus sign right there in the front. So now we're going to find our b squared. B squared equals 6.31 times 10 to the minus 5 squared, which will give us 3.98 times 10 to the minus 9. Next, we're going to find our 4ac, which equals 4 times 1 times 2.524 times 10 to the minus 6. Which is going to equal negative 1.0096 times 10 to the minus 5. So now we're going to subtract our b squared from our 4ac. B squared minus 4ac equals 3.98 times 10 to the minus 9 minus our negative 1.0096 times 10 to the minus 5. After you do that subtraction, you get 1.009981 times 10 to the minus 5. Now we're going to take the square root of that number. So we're going to take the square root of that decimal and do this, right? Yes, this. Copy. Paste. Boom, like magic. Love that. Okay. So once we take that square root, then the number we'll get is, equals 0.0031780467. Big long decimal. Now we can plug that into what's left of our quadratic equation. So we have x equals negative 6.31 times 10 to the minus 5. Because that's our b. Then we have plus or minus our decimal, which is 0.0031780467. All over 2 times 1. 2 times 1. That's going to give us x equals 0.00314947. All over 2, which is going to give us another big long decimal. 0.0015574734. And this number is what's equal to our H plus. Now to find pH, we know that pH equals negative log times our H plus. So pH equals negative log times H plus. pH equals negative log times 0.0015574734. So our pH equals 2.807 or approximately 2.81.
Hey, this is Drew Dixon solving problem 4 in homework 1. So first things first, we're going to write our equation, which is the Henderson-Hasel block. pH is equal to pKa plus the log of A over HA, which is base over acid. Next, we'll be inputting our known variables. We don't know the pH, but we do have the pKa, and we can solve for the acid and base concentrations. Using volume and molarity, we can derive the concentration. We're going to start off with the acid because the acid will be consumed by the strong base, sodium hydroxide. And now we solve. So the logarithm of the big decimal number really rounds out to be 1 over 3, which is negative 0.48. And you don't really need to do any more math after that. pH is 4.22.
This is Juliana Boyette solving question 5 on homework 1. So for this question, we will need the Henderson-Hasselbalch equation, which is pH equals pKa plus log of the concentration of conjugate base over the concentration of weak acid. So we are given pH, which is 7. We are given pKa, which is 7.21. And then we will make an equation to take the place of the concentration of conjugate base and weak acid. So we will use this equation, concentration of weak acid, that's the concentration of conjugate base equals 1. So basically it will add up to the concentration of the solution. So in this case, we want a 0.1 molar buffer. So then we will substitute the conjugate base for X, fill the rest of this in, and then we will solve for HA. And HA will equal 0.1 minus X. So that we will put that in place here. So we will put X over 0.1 minus X. And then we will do some algebra to solve for X. So here, log has a base of 10, so we'll do 10 to the negative 0.21 power equals X over 0.1 minus X. And then that will give us 0.6166 minus X, cross multiply to get 0.06166 minus 0.6166, and then X, or excuse me, 0.6166X here. And then we'll get an X of 0.03814. This X is equal to the concentration of our conjugate base. This will be in moles per liter. And we will multiply by the molar mass of the conjugate base, which in this case it is Na2HPO4. And our molar mass is 141.96. This will be grams per mole. And then we will multiply by the volume of buffer we want. And that will give us, or first we should cancel out our units. And that will leave us with 2.71 grams of our conjugate base. So then we will need to solve for our weak acid. We'll put 0.1 minus 0.03814, and that will give us 0.06186. So for the concentration of weak acid, 0.06186, that'll be moles per liter. We will also multiply it by its molar mass, which in this case, the weak acid is NaH2PO4. We will multiply it by 119.98. This will be grams per mole. Then we'll also multiply by the volume of our buffer. The units will cancel out, and we will be left with a 3.71 grams. So to make our buffer, we will have to add 2.71 grams of our conjugate base and 3.71 grams of our weak acid to get, or excuse me, we will add that with 0.5 liters of water to get our buffer.